Picture this. You're standing under a crystal clear sky. The Milky Way glows above you, billions of stars, each possibly with worlds of their own. Maybe someone out there is looking back, but here's the brutal truth. You will never meet them. Not because we're weak, not because we lack technology, but because the universe has locked us in with one rule: nothing outruns light. Our galaxy is 100,000 light years wide. Even at light speed, you'd need longer than all of human history twice to cross it, and our own radio signals. They've traveled just 90 light years, a microscopic bubble touching 0.0001% of the stars. We haven't contacted the galaxy, we've barely scratched it. If aliens live just 200 light years away, they won't even know we exist for another century, and a simple hello would take 400 years to complete. This is our paradox. The universe is full of stars, and almost completely out of reach. If these cosmic journeys fascinate you every night, don't forget to subscribe to our channel and like the video. This helps the video reach even more people. Thank you in advance. Ready? Then let's begin. Part 1. The Galactic Prison and Why We Desperately Need FTL. The staggering scale of our cosmic cage. Picture this. You're standing in your backyard on a clear night, gazing up at the Milky Way stretched across the sky like a river of light. Thousands of stars twinkle back at you, each one a potential sun with its own family of planets. Maybe somewhere out there, right now, someone else is looking back at you. But here's the cruel twist that keeps astronomers awake at night: you'll never meet them. Not because of technology, not because of funding, but because of something far more fundamental: the speed of light itself. Our galaxy spans more than 100,000 light years from edge to edge. Let that sink in for a moment. If you could somehow travel at the speed of light, the absolute cosmic speed limit, according to Einstein, it would still take you 100,000 years just to cross from one side to the other. That's not a journey. That's geological time. That's the entire span of modern human civilization. Twice over. But wait, it gets worse. Way worse. Even humanity's earliest radio transmissions, which have been racing through space at light speed since the 1930s, have barely made a dent in our cosmic neighborhood. We're talking about signals that have traveled for nearly 90 years, covering roughly 90 light years in every direction. Sounds impressive, right? Wrong. That bubble of human radio noise has washed over less than 1,000,000,001% of the stellar population in our galaxy. We've essentially announced our presence to a rounding error of stars. Think about what that means for a second. If there's an alien civilization just 200 light years away, practically next door in galactic terms, they won't even know we exist for another 110 years. And if we wanted to have a conversation with them, we'd send a message, wait 200 years for it to arrive, then wait another 200 years for their response. That's a 4-hour round trip for a simple hello. Your great-great-great-great-great-grandchildren might get to hear the reply to your message. This is the cosmic speed limit we're dealing with. Light travels at approximately 186,000 miles per second, fast enough to circle the Earth 7.5 times in a single second. Yet, when measured against the vast ocean of space, this seemingly infinite velocity becomes pathetically inadequate. It's like trying to cross the Pacific Ocean in a rowboat. Sure, you're moving, but the scale of your challenge makes your effort almost laughable, trapped behind invisible bars. Here's where it gets emotionally brutal. We live in a universe that seems specifically designed to taunt us. Nature has given us eyes that can detect light from galaxies billions of light years away. We've built telescopes that can peer back to within 400 million years of the Big Bang itself. We can see exoplanets orbiting distant stars, detect the chemical composition of their atmospheres, even identify potential biomarkers that might indicate life. We've glimpsed the treasures of the cosmos in stunning detail, but we can't touch them. We can't reach them. We can only look. It's the ultimate cosmic prison. Imagine being locked in a room where every wall is a window, and through those windows, you can see everything: beautiful landscapes, fascinating people, entire civilizations, but you can never, ever step outside. You can watch, you can study, you can dream, but you can never participate. That's humanity's situation on a cosmic scale. The light speed barrier isn't just a limitation, it's a cage. And unlike every other barrier humanity has ever faced, this one seems absolutely fundamental to the structure of reality itself. We've conquered the air, the oceans, even touched the moon and sent probes to the outer reaches of our solar system. But interstellar space, That's a different beast entirely. Consider the Voyager 1 spacecraft, humanity's most distant ambassador. Launched in 1977, it's been traveling for nearly 50 years and has finally entered interstellar space. It's roughly 15 billion miles from Earth, the farthest any human-made object has ever traveled. That's an incredible achievement, a testament to human ingenuity and persistence. But here's the kicker. Voyager 1 is traveling at about 38,000 miles per hour. And at that speed, it would take over 70,000 years to reach Proxima Centauri, our nearest neighboring star system, which sits just over 4 light-years away. 70 years to reach our closest neighbor. Do you see the problem? The gap between what we can achieve and what we need to achieve isn't just large, it's laughably, impossibly, devastatingly large. We're not even in the same ballpark. We're not even playing the same sport, the dream that won't die. Ever since I was a kid, maybe 5 or 6 years old, I've looked up at the night sky and felt this overwhelming longing. Not just curiosity, not just wonder, actual longing, the kind you feel when you're separated from something you love. Those points of light weren't just pretty decorations to me. They were places, real places where real things were happening, where alien sunsets painted strange skies in colors we've never named, where life might be thriving in forms we can't even imagine. I wanted to go there. Not in some abstract, wouldn't that be nice kind of way. I wanted to board a ship, strap in, and actually go. I wanted to explore the ocean of space like the explorers of old explored Earth's oceans. I wanted to catalogue the zoo of worlds that must exist out there: ice planets and lava planets, ocean worlds and desert spheres, gas giants with storms that could swallow our entire planet. I wanted to discover the menagerie of life in all its weird, wonderful forms, maybe silicon-based creatures on high-temperature worlds, or vast colonies of intelligent fungi communicating through spores, or things so alien we don't even have the vocabulary to describe them, but the light speed limit stands in the way. Always thought it feels like nature is playing a cruel joke on us. Here, the universe seems to say, look at all these wonders I've created. Look at these billions of galaxies, each containing billions of stars, each potentially hosting billions of planets. Look at all these possible homes for life, for civilization, for minds that might be pondering the same questions you are. But you can't reach them. You can only wonder, is there any technology more desperately needed than faster than light travel? Is there any breakthrough that would more fundamentally transform the human condition? FTL wouldn't just be a convenience, like a faster airplane or a better computer. It would redefine what it means to be human. It would transform us from a single planet species staring longingly at the stars to a truly galactic civilization. FTL would mean that the teenager born today could, within their lifetime, walk on a planet orbiting Alpha Centauri. It would mean we could search for life not by analyzing distant spectra, but by actually going and looking. It would mean that humanity's story doesn't have to be confined to one tiny blue marble in the suburbs of an ordinary galaxy. The stubborn human spirit. Here's the thing about humans: we've never been particularly good at accepting limitations. Tell us something is impossible, and we'll spend the next 100 years proving you wrong. Heavier than air flight. Impossible, they said, right up until the Wright brothers proved otherwise. Breaking the sound barrier, pilots would be torn apart, physicists warned, until Chuck Yeager did it anyway. Splitting the atom, landing on the moon, computing machines small enough to fit in your pocket. All impossible, until they rearranged single quotes to when Einstein showed up in 1905 with his special relativity and declared that nothing with mass could ever reach, let alone exceed, the speed of light. Did humanity just accept it and move on? Hell no. We've spent the last 120 years looking for loopholes, searching for exceptions, exploring the boundaries of what it really means. This isn't stubbornness for stubbornness' sake. This is the same drive that got our ancestors to leave the safety of caves and explore unknown continents. It's the same curiosity that pushes sailors to venture beyond the horizon even when everyone knew they'd fall off the edge of the world. It's fundamental to who we are as a species, and you know what? Sometimes that refusal to accept limits pays off in unexpected ways. We might not be able to break the light speed barrier through brute force, but what if there are ways around it? What if the problem isn't that we need to go faster, but that we're thinking about motion in the wrong way entirely? That's where things get interesting, because while Einstein's equations might forbid faster than light travel through space, they don't say anything about the motion of space itself. Let that distinction settle in your mind for a moment. We can't move through space faster than light, but space itself faces no such restriction. When space itself becomes the vehicle, this is where cosmology offers us a tantalizing hint. A crack in what seemed like an impenetrable wall. Look far enough into the distant universe, and you'll find galaxies receding from us at velocities that exceed the speed of light. These aren't objects moving through space faster than light, that's still forbidden, but rather objects being carried away by the expansion of space itself. Space can stretch, compress, warp, and bend. Einstein taught us that much. Gravity itself is nothing but the curvature of spacetime around massive objects. So if space can bend around a star, if it can stretch between galaxies, could we somehow learn to manipulate it? Could we convince space to work for us rather than against us? This isn't science fiction anymore, at least. Not entirely. These are questions serious physicists are exploring. Threads they're pulling on to see where they lead. Maybe one day, probably not in our lifetimes, but perhaps in our grandchildren's. One of those threads will lead somewhere real. Maybe one day, someone will figure out the trick, the hack, the exploit in the cosmic code that lets us slip past the light speed barrier. Because if there's one thing human history teaches us, it's this: the impossible just takes a little longer. But before we get too carried away with optimism, we need to talk about the serious problems facing FTL. Not engineering problems, those we could probably solve with enough time and resources. No, I'm talking about fundamental issues with the fabric of reality itself. Problems so deep and so troubling that they might mean FTL isn't just difficult. IT might be truly impossible. And the reason why is more mind-bending than you might imagine. Because it turns out that faster than light travel isn't just a physics problem, it's a causality problem. FTL and time travel are the same thing, and that connection brings with it some deeply disturbing implications that we need to understand. But we're getting ahead of ourselves. First, let's talk about what physicists have actually proposed when it comes to FTL systems, and why each one seems to run into the same fundamental roadblocks, the reality check we need. Let me be crystal clear about something before we go any further. We currently have no way to build a faster than light system. Not even close. We don't have a prototype sitting in a lab somewhere waiting for better funding. We don't have a theoretical design that just needs some engineering work. We don't even have a clear conception of how such a system would work that doesn't immediately run into show-stopping problems. This isn't a failure of imagination or effort. Some of the brightest minds in physics have tackled this question for decades. They've explored every angle, every loophole, every possible interpretation of Einstein's equations. And while they've found some fascinating possibilities, ideas that make for great science fiction, and might even work in principle, none of them translate into anything remotely practical. But here's where it gets interesting. There are threads, theoretical concepts that don't violate any known laws of physics. They might not be buildable with our current technology, or with any technology we can currently imagine, but they're not forbidden by the equations that govern reality. At least, not by the equations we know about. These threads are worth exploring not because they'll lead to FTL starships next year, but because they teach us about the deep structure of spacetime itself. They reveal the strange flexibility and rigidity of the universe, the places where reality bends and the places where it refuses to budge. And occasionally, just occasionally, exploring these theoretical ideas leads to unexpected practical applications. Nobody studying quantum mechanics in the 1920s thought it would lead to smartphones and GPS satellites. Nobody exploring Maxwell's equations in the 1860s imagined wireless communication. Sometimes understanding fundamental physics leads to technologies that seem like magic. Could FTL be one of those cases? Honestly, probably not. The barriers seem too fundamental, too deeply embedded in the structure of cause and effect itself. But then again, the universe has surprised us before. What matters is that we keep asking the question, keep pushing at the boundaries, keep looking for those loopholes. Because the alternative, accepting our cosmic imprisonment without even trying to find a way out, that's not who we are as a species. The dream won't die. It can't die. As long as there are humans who look up at the stars and feel that longing, that fundamental desire to explore and discover, we'll keep searching for a way to break free from our cosmic cage, even if that way turns out to be impossible. Now, let's talk about what physicists have actually proposed, starting with the most famous FTL concept of all, the Alcubierre drive. This is where things start getting weird, and where we begin to see why FTL might be fundamentally incompatible with the universe we live in. Part 2. FTL systems' theoretical possibilities and engineering nightmares. The loophole Einstein left behind. Here's something that blows most people's minds when they first hear it. Einstein's cosmic speed limit doesn't actually apply to everything. Yeah, you heard that right. The famous rule that nothing can travel faster than light. It's got a loophole big enough to drive a spaceship through theoretically, at least. The trick is in the fine print. Einstein's special relativity says that nothing can move through space faster than light. Through space. Those two words are absolutely critical, because they don't say anything about the motion of space itself. It's like the difference between swimming across a river and being carried by the current. You might be a slow swimmer, but if the river's moving fast enough, you can still cover serious distance. Space itself has no speed limit whatsoever. We know this isn't just theoretical wordplay because we can actually observe it happening right now. Look deep enough into the universe, far beyond our local galactic neighborhood, and you'll find galaxies rushing away from us at velocities that make light look like it's standing still. These distant galaxies aren't violating Einstein's rules because they're not really moving through space at all. Space itself is expanding, carrying them along for the ride. The universe has been doing this since the Big Bang, roughly 13.8 billion years ago. In the first fraction of a second after creation, space expanded so rapidly that regions of the universe were separated faster than light could ever hope to cross between them. This period, called cosmic inflation, stretched space faster than anything moving through it could possibly keep up with. So here's the million-dollar question. If space can move that fast naturally, could we learn to control it? Could we create our own little bubble of expanding and contracting space and ride it across the galaxy? That's not science fiction. That's a legitimate question that physicists are seriously exploring. And the most famous answer to that question came from a physicist who was inspired by one of the most iconic science fiction shows ever made, the Star Trek solution. In 1994, a Mexican theoretical physicist named Miguel Alcubierre was watching Star Trek and thinking about warp drive, the fictional technology that lets the Enterprise zip around the galaxy visiting a new planet every week. Most physicists would dismiss this as pure fantasy and move on with their day. But Alcubierre asked himself, is there any way this could actually work within Einstein's equations? What he discovered shocked the physics community. Alcubierre found an exact solution to Einstein's field equations, the mathematical framework that describes how gravity and spacetime interact that could, in principle, allow faster than light travel, not by breaking the light speed barrier, but by going around it entirely. Here's how it works. Imagine you're inside a bubble of normal spacetime. Behind your bubble, space expands rapidly, pushing you forward. In front of your bubble, space contracts, pulling you toward your destination. You're not moving through space at all, you're sitting perfectly still inside your bubble while space itself does all the work. The bubble can move as fast as you want it to. 10 times light speed? Sure. 1,000 times? Why not? There's no limit because the bubble isn't traveling through space. It's surfing on space itself. From your perspective inside the bubble, time flows normally. You don't experience time dilation. You don't age any differently than you would on Earth. And you don't need to worry about relativistic effects. You could travel to a star 100 light years away, spend a few months in transit from your perspective. And when you arrived, only a few months would have passed on Earth too. No twin paradox, no time travel weirdness, just straight up FTL travel that respects causality at least. That's what the math says. The physics community went absolutely wild when Alcubierre published his paper. Here was actual proof, written in the language of general relativity, that warp drive wasn't just science fiction. It was mathematically possible. Star Trek had gotten something right, and now physicists had to take the idea seriously. But and this is a huge but mathematically possible doesn't mean practically achievable. Not even close, the deal breakers nobody mentions. Let's talk about what it would actually take to build an Alcubierre drive, because this is where the dream crashes hard into reality. First problem: exotic matter. To create the kind of space-time distortion needed for the Alcubierre bubble, you need something with negative mass energy. Not antimatter, that's different. We're talking about matter with less than zero energy. Something that repels rather than attracts gravitationally. It's called exotic matter. And here's the thing. We've never seen it, never created it. And we're not even sure it can exist. Some physicists point to the Casimir effect as evidence that negative energy densities might be possible in quantum field theory. But even if that's true, The amounts involved are absurdly tiny, nowhere near enough to warp spacetime on the scale needed for a functioning warp drive. Second problem: energy requirements. When physicists first calculated how much energy you'd need to create an Alcubierre bubble large enough to contain a spaceship, they came up with a number equivalent to the entire mass energy of Jupiter. That's roughly 318 times Earth's mass, converted completely into energy. We're talking about an energy budget that would require us to disassemble an entire gas giant and convert it into pure power with 100% efficiency over the years. Clever physicists have found ways to reduce these requirements by tweaking the shape and properties of the bubble. Some designs got it down to the mass energy of a small planet, then a mountain, then a Voyager-sized spacecraft. That's progress, right? Except even converting a single spacecraft's mass into energy completely would still require technology so far beyond our current capabilities that it might as well be magic. Third problem: the radiation problem. Here's something nasty that emerged when physicists started thinking about what happens to particles and radiation as your warp bubble moves through space. As the bubble travels, it accumulates particles and radiation along its leading edge. These get blue-shifted to incredibly high energies, building up into a devastating wave of gamma rays and high-energy particles when you arrive at your destination and turn of the warp drive. All that accumulated radiation gets released in a catastrophic burst directed straight ahead. You'd essentially turn your destination into a blast furnace, sterilizing anything in front of you with a death ray containing more energy than multiple nuclear weapons. Imagine using your FDL drive to visit an inhabited planet and accidentally destroying it the moment you arrive. That's not a great first contact scenario, but none of these are actually the real deal breaker. Engineers are optimists. Give them a problem, and they'll figure out a solution, even if it takes centuries. Energy requirements. Maybe future civilizations will figure out stellar scale engineering. Exotic matter. Perhaps quantum field manipulation will crack that nut. Radiation problems. We could engineer around them. Maybe use magnetic fields or exotic matter shields to redirect the buildup. The real problem with the Alcubierre drive is far more fundamental. It's about what happens when you bring quantum mechanics into the picture. When quantum effects crash the party. Einstein's general relativity, which gives us the Alcubierre solution, is a classical theory. It treats spacetime as a smooth, continuous fabric that can be bent and warped by mass and energy. But we know that's not the whole story. At tiny scales, spacetime itself is subject to quantum fluctuations, and matter and energy behave according to the weird rules of quantum mechanics, not classical physics. The problem is, we don't have a complete theory that unifies quantum mechanics and general relativity. Physicists call this missing piece quantum gravity, and it's one of the biggest unsolved problems in all of physics. We can do quantum field theory in curved spacetime, which gives us some insights, but we don't have the full picture. And when physicists started asking what quantum effects would do to an Alcubierre drive, they found something alarming. In 2009, a physicist named Stefano Fanazzi showed that the warp bubble would generate Hawking radiation, the same kind of radiation that Stephen Hawking predicted would cause black holes to slowly evaporate. But here's the kicker. This radiation doesn't just leak out slowly. It builds up exponentially inside the bubble. Exponential growth is terrifying. It starts small, doubles again, and before you know it, you've got numbers that shoot off to infinity. The Hawking radiation inside an Alcubierre bubble would rapidly reach energies so intense that it would fry anything inside and, more importantly, destabilize the bubble itself. Your warp drive would tear itself apart from the inside. Now, you might think, okay, but we don't really understand quantum gravity yet. So maybe when we figure that out, we'll find this isn't actually a problem, and you'd be half right. We don't understand quantum gravity fully, but that cuts both ways. Every time physicists have included quantum effects in calculations about exotic spacetime structures, those effects have made things worse, not better. The wormhole problem. The Alcubierre drive isn't the only game in town when it comes to FDL concepts. Another classic idea from general relativity is the wormhole, a tunnel through spacetime that connects two distant locations. Walk in one end, walk out the other, and boom, you've crossed light years in a few steps. Einstein and Nathan Rosen first described this concept back in 1935, calling them Einstein-Rosen bridges. The math works. General relativity allows for these structures. They're solutions to Einstein's equations just like the Alcubierre metric, but they face the exact same problems. First, you need exotic matter to hold the wormhole open. Without it, the tunnel would collapse faster than anything could pass through it. Second, you need enormous energies to create and maintain the structure. And third, you guessed it, quantum effects probably kill the whole idea. When physicists try to account for quantum fluctuations in the spacetime around a wormhole, they find that these fluctuations would likely cause the wormhole to pinch off and explode. The vacuum itself would become unstable, flooding the wormhole with energy and destroying it. Some theorists have proposed solutions. Maybe you could use exotic matter to stabilize against quantum fluctuations. Or maybe there are configurations that are naturally more stable. But we're piling speculation on top of speculation here. Using physics we don't fully understand to solve problems in regimes where our current theories break down. The kitchen sink of FTL ideas. The list of proposed FTL mechanisms goes on, each with its own flavor of promise and problems. Let's rapid fire through some of them. Tachyons. Hypothetical particles that always travel faster than light, never slower. The math allows for them, but if they existed, they create causality violations and would probably be impossible to detect or interact with in any useful way. Krasnikov tubes. Another spacetime manipulation idea where you lay down a tube of warped space behind you as you travel at relativistic speeds. Future travelers could then use the tube to make the return journey much faster. Clever, but it doesn't help the first traveler. And it still requires exotic matter and enormous energies. Quantum tunneling. In quantum mechanics, particles can occasionally tunnel through barriers they shouldn't classically be able to cross. Could something similar allow information or matter to tunnel across interstellar distances? Maybe, but every analysis so far suggests that any tunneling FTL would still respect the light speed limit when you properly account for when information is actually received. Quantum entanglement. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Could we use this for FTL communication? Unfortunately, no. The correlations in entanglement can't be used to send information faster than light without violating the no communication theorem of quantum mechanics. It's frustrating, but it's airtight. Each of these ideas has been explored, tweaked, modified, and optimized by physicists looking for a way to make them work. And each one either requires exotic physics we've never observed, or runs into quantum stability problems, or both. The optimist perspective. Now, before you sink into complete despair, let's consider the optimist's viewpoint. None of these problems are definitive proof that FTL is impossible. They're engineering challenges, admittedly. Extraordinary engineering challenges that might require civilizations far more advanced than ours to solve, but challenges nonetheless. Not absolute barriers. Maybe exotic matter exists and we just haven't figured out how to create it yet. Maybe there are quantum field configurations that can stabilize warp bubbles or wormholes. Maybe there's some clever workaround we haven't thought of, hiding in the mathematics of theories we haven't developed yet. After all, imagine trying to explain semiconductors to someone in 1850. They'd look at you like you were insane. You want to make rocks that can think? You want to control the flow of individual electrons through crystal lattices? You're talking nonsense. Yet here we are, with billions of transistors in every smartphone, doing exactly that. Could FTL be similar? Could it just require a level of technological and theoretical sophistication we haven't reached yet? Maybe, but here's the uncomfortable truth. There's a fundamental difference between the engineering challenges of building a computer and the challenges facing FTL. One requires understanding and manipulating matter and energy in clever ways. The other might require breaking the logical structure of cause and effect itself, the real problem nobody wants to face. All these engineering challenges, exotic matter, energy requirements, quantum instabilities might actually be symptoms of a deeper problem. What if the universe is trying to tell us something? What if every FTL system runs into these impossible barriers because FTL itself is fundamentally incompatible with how reality works? There's a reason that every FTL concept faces similar roadblocks. It's not bad luck. It's not that physicists aren't being creative enough. It's because there might be something deeply wrong with the entire concept of faster than light travel, and that something has to do with causality, the relationship between cause and effect. We're used to thinking about causality violations as time travel paradoxes, grandfather paradoxes, that sort of thing. But here's what most people don't realize. You don't need a time machine to create causality violations. You don't need to travel backward through time at all. All you need is FTL. Any FTL system, No matter how it works, warp drives, wormholes, tachyons, whatever automatically gives you time travel. And with time travel comes all those nasty paradoxes that make physicists wake up in cold sweats. This isn't obvious at first. It requires understanding how relativity really works, how different observers moving at different speeds experience time and simultaneity differently. It requires thinking carefully about spacetime diagrams and reference frames, but once you see it, you can't unsee it. FTL and time travel are the same thing. And if time travel paradoxes are impossible, which they better be, or the entire logical structure of the universe falls apart, then FTL might be impossible too, not for engineering reasons, for fundamental, logical, reality-breaking reasons. And that's what we need to talk about next. We need to understand exactly why FTL implies time travel, why that's such a massive problem, and what it might mean for our dreams of exploring the galaxy. But to understand that, we first need to learn a new way of visualizing spacetime, a tool that will let us see with perfect clarity why faster than light travel creates paradoxes that might tear apart the fabric of causality itself. Get ready. Things are about to get weird. Part 3. Spacetime diagrams, the map that reveals everything. The language of the universe. All right, buckle up. We're about to learn a new way of looking at reality, a visual language that lets us see the deep structure of spacetime itself. This isn't just abstract mathematics or ivory tower theorizing. This is a tool that will let you see, with your own eyes, why FTL travel creates time travel paradoxes. Once you understand this, you'll have a superpower that most people lack. The ability to visualize how different observers experience time and space differently. Sound complicated? It's actually surprisingly intuitive once you get the hang of it. We're going to build this understanding step by step, starting with the basics and working our way up to the mind-blowing stuff. By the end of this section, you'll be able to look at a spacetime diagram and immediately spot causality violations that would take pages of equations to describe mathematically. So let's start simple. Forget about relativity for a moment. Just think about how you draw a map of where things are and when things happen. Imagine you're watching a car drive down a straight highway. You could draw the highway as a horizontal line, with position marked along it, 0 miles at one end, 100 miles at the other. That's space, one dimension of it anyway. Now, you also want to show when the car is at each position, so you add a vertical axis representing time. 0 at the bottom, 1 hour at the top, 2 hours above that, and so on. Now, you can plot the car's journey as a line on this graph. If the car starts at mile 0 at time 0 and drives to mile 60 in 1 hour, you draw a diagonal line connecting those 2 points. That line tells you everything about the car's journey, where it was at every moment in time. Congratulations. You've just drawn your first spacetime diagram. That diagonal line. Physicists call it a world line. It's not the car itself, it's the complete history of the car's motion through space and time. This is how we're going to visualize FTL and causality. Not with equations, but with pictures that show the entire history of events laid out in front of us, building our cosmic canvas. Let's make this more cosmic. Instead of a highway with a car, let's think about space with stars in it. We'll draw one dimension of space horizontally along the bottom of our diagram. Let's call it the x-axis. This represents distance. 0 in the middle, positive numbers to the right, negative to the left. We could measure it in light years, miles, whatever we want. Now we add time as our vertical axis. 0 at the bottom represents now, or whatever moment we want to call the present. Positive time values going up represent the future. We could even add negative times going down to represent the past. Though we won't need that for what we're doing. We now have a coordinate system that can describe any event, anything that happens at a specific place and a specific time. The explosion of a supernova, the birth of a star, a spaceship reaching a planet, all of these are events. Points on our spacetime diagram. Let's put some actual objects on this diagram. Take Vega, one of the brightest stars in the night sky, about 25 light years from Earth. We'll represent Vega's location in space as a point on our horizontal axis. Let's say it's 25 light years to the right of center. Now, Vega isn't moving much relative to Earth, it's pretty much stationary in our reference frame, so as time progresses upward, Vega stays at the same position. Its world line is a vertical line, parallel to the time axis. Same deal with Earth. We'll put it at the center, at 0 on the space axis. Earth's not moving in this reference frame either, so its world line is also vertical, parallel to Vega's. 2 vertical lines, 25 light years apart. representing two stationary objects moving through time. This is the power of spacetime diagrams. They let us see both space and time at once, as a unified whole. Einstein showed us that space and time aren't separate things, they're woven together into spacetime. And these diagrams make that connection visual and concrete. The geometry of speed. Now let's talk about motion, because understanding how speed looks on these diagrams is absolutely crucial for everything that comes next. If you're sitting still in this reference frame, say, you're hanging out on Earth, you're not moving through space, but you are moving through time. Every second, you advance 1 second into the future. Your world line goes straight up, parallel to the time axis. The steeper your world line, the less you're moving through space. What about something moving through space? Let's say a spaceship launches from Earth and travels toward Vega at half the speed of light. Its world line would be a diagonal line, tilted at an angle. The faster it goes, the more horizontal that line becomes. A slow ship has a steep line, close to vertical. A fast ship has a shallow line, closer to horizontal. Now here's the key question. What does the speed of light look like on this diagram? Light has a special property. It always travels at the same speed, roughly 186,000 miles per second, or about 671 million miles per hour. Or if you prefer, 1 light year per year. That last unit is actually perfect for spacetime diagrams because it makes the math incredibly clean. If you draw your diagram with distance in light years and time in years, then light travels at 45-degree angles. A beam of light leaving Earth and heading toward Vega would trace out a diagonal line at exactly 45 degrees. A beam heading the other way would be a 45-degree line in the opposite direction. Physicists call these 45-degree lines null lines because along them, the spacetime interval, a measure of separation in spacetime, equals 0. But don't worry about the terminology. Just remember, on a properly scaled spacetime diagram, light always travels at 45-degree angles. This gives us an incredibly useful tool for understanding what's possible and what's not, the forbidden zone. Here's where things get interesting. Draw those 45-degree null lines extending upward from Earth, one going up and to the right, one going up and to the left. These represent light beams spreading out from Earth in both directions. Everything between those two null lines represents possible futures that Earth can influence using slower than light signals or ships. If you want to send a message to something in this region, you can. If you want to send a spaceship there, you can. Any world line that stays within this fish-shaped region respects the cosmic speed limit. But what about the regions outside the V? The areas to the left and right, beyond the null lines. Those regions are causally disconnected from Earth's present moment. Nothing moving slower than light can reach them from here and now. They're unreachable, at least without FTL. An FTL signal would have a world line that breaks through those 45-degree barriers. It would be more horizontal than the null lines, less steep, more diagonal. The more horizontal, the faster the signal. A truly instantaneous signal would be completely horizontal, parallel to the space axis, covering distance with 0 time elapsed. You can immediately see why this is called a speed limit. The null lines act like barriers. Slower than light motion keeps you inside them. Faster than light motion breaks through them. And as we'll see, breaking through those barriers has consequences that go way beyond just traveling fast. The hidden rules of spacetime. Before we move on to the really mind-bending stuff, we need to establish 2 crucial relationships that govern spacetime diagrams. These are going to seem simple, maybe even obvious, but they're absolutely essential for understanding what comes next. Rule number 1. The world line of an object defines that object's time axis. Think about it. If you're sitting still in a reference frame, your world line goes straight up, parallel to the time axis of that frame. From your perspective, you're not moving through space, you're just sitting there while time ticks forward. So your personal experience of time, your subjective time axis, is the same as your world line. This seems trivial when you're stationary, but it becomes crucial when you're moving. A spaceship traveling at relativistic speeds has a tilted world line, and that tilted line represents the crew's experience of time. Their clocks, their aging, their sense of now, all of it flows along that tilted world line. Rule number 2. The space axis is a reflection of the time axis around the null line. This one's more subtle. If you take the time axis and flip it around the 45-degree null line, you get the space axis. They're mirror images of each other with the null line as the mirror. For someone at rest in a reference frame, their time axis is vertical, and their space axis is horizontal, perpendicular to each other. Just like you'd expect, but here's the weird part. For someone moving, both their time axis and their space axis tilt. If their world line, their time axis tilts one way, their space axis tilts the opposite way around the null line. The faster they're moving, the more both axes tilt. Why does this matter? Because the space axis defines simultaneity. Events that lie along the space axis are, from that observer's perspective, happening at the same time, and when different observers have different tilted space axes, they disagree about what at the same time even means. This is where relativity gets weird. And this is exactly the weirdness that creates causality violations when you introduce FTL. Drawing the scene. Let's set up a scenario that we'll use to demonstrate the causality problem. We need a few ingredients: Earth, a distant star, and an event that we want to communicate about. We've already got Earth at the center of our diagram, and Vega off to the right, 25 light years away. Both have vertical world lines representing their motion through time. They're not moving relative to each other, so from both Earth's and Vega's perspectives, the time and space axes are the standard perpendicular ones. Now let's add an event. Imagine a supernova explodes somewhere between Earth and Vega. Let's call it Supernova X. We'll place it closer to Earth than to Vega. Maybe 10 light years from Earth and 15 light years from Vega. The supernova happens at a specific place and time, so it's a single point on our spacetime diagram. When the supernova explodes, it emits light in all directions. That light travels along null lines, 45-degree diagonals spreading out from the explosion point. One null line heads toward Earth, another toward Vega. We can trace these null lines and see where they intersect Earth's and Vega's world lines. Those intersection points represent when each location sees the supernova. Since X is closer to Earth, the null line reaches Earth first. Let's say Earth sees it after 10 years. Then the light continues on and reaches Vega after another 15 years. For a total of 25 years after the explosion. So far, everything makes perfect sense. Cause and effect flow in the right direction. The supernova happens first, then Earth sees it, then Vega sees it. No problems whatsoever. Adding the FTL element. Now let's introduce an FTL communication system. Imagine that the moment Earth sees supernova X, Earth decides to send a warning message to Vega using faster than light communication. Maybe we've got an Ansible, or a tachyon transmitter, or a wormhole-based communicator, doesn't matter which. The point is, the message travels faster than light on our spacetime diagram. This FTL message is represented by a line that's more horizontal than the 45-degree null line. It starts at the point where Earth sees the supernova and ends where it reaches Vega. Because it's traveling faster than light, it arrives at Vega before the light from the supernova does. Mission accomplished, right? Earth saw the supernova and warned Vega before Vega saw it naturally. That seems like a perfectly reasonable use of FTL communication. No paradoxes, no problems, just a useful heads up about an approaching blast of radiation. And if we look at the order of events from Earth's perspective, everything checks out. Let's trace through time by imagining a horizontal line, a line of simultaneity sweeping up the diagram from bottom to top, showing us events in the order that Earthlings experience them. First, supernova X explodes. The sweep line crosses that event first. Second, Earth sees the supernova and sends the FTL warning. Third, Vega receives the warning. Fourth, Vega sees the supernova itself. Perfectly sensible. Cause precedes effect every single time. Vega's perspective, same order of events. They're at rest relative to Earth, so they share the same notion of simultaneity, the same time axis. From their viewpoint, the sequence is identical. Explosion, Earth sees and warns. Vega receives warning. Vega sees explosion. Everything looks fine. No causality violations. FTL seems perfectly safe. So what's the problem? The observer that changes everything. The problem is that Earth and Vega are at rest. They're not moving relative to each other, so they share a common reference frame. Of course, everything looks fine from their perspective. We designed the scenario that way. But what happens if we add a third observer, one who's moving at a significant fraction of light speed? Say, a spaceship traveling from Earth toward Vega at 80% of light speed. This is where everything falls apart. Remember rule 1. The ship's world line defines its time axis. The ship is moving, so its world line is tilted not vertical like Earth and Vega, but diagonal, angled toward the right since it's heading toward Vega. That tilted line is the ship's experience of time. And remember rule 2. The space axis reflects the time axis around the null line. So if the ship's time axis tilts one way, its space axis tilts the opposite way. For this ship moving at 80% light speed, the space axis tilts significantly, maybe 40 degrees from horizontal instead of being perfectly horizontal. That tilted space axis defines what the ship considers to be simultaneous, what events it considers to be happening at the same time. And here's where things get absolutely bonkers. To see the order of events from the ship's perspective, we need to sweep our simultaneity line, now tilted to match the ship's space axis from bottom right to top left across the diagram. This shows us the sequence of events as experienced by the ship's crew, and when we do this, something shocking happens. The universe turned upside down. Let's trace through the events in order from the ship's perspective, using the tilted simultaneity lines. The first event that the ship's crew sees: Vega receiving the warning message from Earth. That's event number 1 in their timeline. Wait, what? How can Vega receive the message before anything else happens? Keep going. The second event: Supernova X explodes. Third, Earth sees the supernova and sends the warning. Fourth, Vega sees the supernova with its own telescopes. Do you see the problem? From the ship's perspective, Vega received the warning message before Earth sent it. The effect happened before the cause. Causality is broken. But how is this possible? How can two different observers disagree so fundamentally about the order of events? Is one of them wrong? No, they're both right. This is relativity in action. When events are separated by space-like intervals, when they're far enough apart in space and close enough together in time that light couldn't connect them, different observers moving at different speeds will disagree about which event happened first. In everyday life, we never notice this because the speed of light is so enormous compared to the speeds we typically move at. The disagreements are measured in billionths of a second at most. But when you're dealing with FDL communications spanning light years and observers moving at relativistic speeds, those disagreements become impossible to ignore, and they lead to paradoxes. The sanity check. Now, you might be thinking, maybe the problem isn't FDL. Maybe the problem is relativity itself. Maybe Einstein got something wrong, and that's why we're seeing these weird causality violations. Fair question. Let's test it. Let's remove the FDL message and see what happens. Go back to our diagram with Earth, Vega, Supernova X, and the relativistic ship. But this time, Earth doesn't send any FDL warning. The only signals are light speed signals, the radiation from the supernova itself. Now let's trace through events from the ship's perspective using those tilted simultaneity lines. First event: Supernova X explodes. Second, Earth sees it. Third, Vega sees it. The order makes perfect sense. No causality violations at all. And notice, this is the same order that Earth and Vega observe. Everyone agrees on the sequence when only light speed signals are involved. So the causality violation doesn't come from relativity. It comes specifically from adding FDL communication to a relativistic universe. Relativity is fine. Light speed communication is fine. But FDL plus relativity equals causality violation. You cannot have both. Does it really matter? At this point, you might be thinking, okay, so different observers disagree about the order of events. That's weird, sure, but does it actually matter? Maybe causality is more flexible than we thought. Maybe the universe can handle a little disagreement about timing. That would be nice, wouldn't it? If this were just an academic curiosity, something that made philosophers scratch their heads but didn't have any real consequences. Unfortunately, it's not. This disagreement about event ordering isn't just philosophically troubling, it can be weaponized to create actual paradoxes that threaten the logical consistency of the universe itself. And we can prove it with one simple addition to our scenario. Let the ship's crew respond instead of being passive observers. Imagine the ship has its own FDL transmitter. When they receive Earth's warning about the supernova, which, remember, from their perspective happens before Earth even sends it, they decide to send a reply back to Earth. Let's say they send a message saying, "Thanks for the warning. By the way, don't bother sending it. That reply message is also FDL, so it also travels on a line more horizontal than the null lines. And because of the way the ship's reference frame is tilted, that reply message, when viewed in Earth's reference frame, travels backward in time. The reply arrives at Earth before Earth sent the original message. Earth receives a message saying, don't send the warning. So they don't send it. But if they don't send it, the ship never receives it. So they never send the reply. so Earth never receives the instruction not to send the message. So they do send it, and around we go. It's the grandfather paradox. But with FTL communication instead of time machines, you've created a logical loop that contradicts itself, a paradox that cannot be resolved. The universe doesn't just bend, it breaks. The stark reality. This isn't speculation. This isn't some obscure edge case that requires contrived circumstances. This is a fundamental, unavoidable consequence of combining FTL with special relativity. Any FTL system, warp drives, wormholes, tachyons, Ansible, whatever gives you time travel. And time travel gives you paradoxes. And paradoxes give you logical contradictions that shouldn't exist in a rational universe. You can draw the diagrams yourself. Pick any FTL mechanism you like. Add two observers in different reference frames. Let them exchange FTL messages. You'll always find a way to create a causal loop if you try. This is why physicists take this problem so seriously. It's not about engineering limitations. It's not about energy requirements or exotic matter. It's about whether the universe itself can remain logically consistent, and that's a much harder problem to solve than figuring out how to bend spacetime. Part 4. The causality catastrophe when FTL breaks reality. The paradox that cannot exist. Let's hammer this home with crystal clarity, because what we're about to explore isn't just some theoretical curiosity, it's a fundamental threat to the logical structure of reality itself. We've seen how FTL communication can create situations where different observers disagree about the order of events. Now we're going to see how that disagreement can be weaponized to create actual, honest-to-God time travel paradoxes, and we're going to do it with the simplest possible setup. No fancy technology, no exotic physics beyond the FTL communicators themselves. Just two FTL messages and the unavoidable consequences of special relativity. Here's the scenario one more time, but now we're going to follow it all the way to its logical conclusion. Earth detects supernova X and sends an FTL warning to Vega. A relativistic spaceship traveling from Earth toward Vega intercepts this message. The ship's crew, having received the message, decides to send an FTL reply back to Earth. What does that reply say? Let's make it maximally paradoxical. The message says, "Turn off your FTL transmitter. Do not send this message." Now, where does this reply appear on our spacetime diagram? Remember, we're drawing everything from Earth's reference frame, the frame where Earth and Vega are stationary and have vertical world lines. In this frame, the ship is moving, so its reference frame is tilted. When the ship sends an FTL message back toward Earth, that message travels faster than light in the ship's reference frame. But because the ship's frame is tilted relative to Earth's frame, something bizarre happens. When you translate that FTL world line from the ship's frame back into Earth's frame, it tilts backward in time. The message arrives at Earth before Earth sent the original warning. Let me say that again, because it's crucial in Earth's own reference frame. Looking at Earth's own clocks, the reply arrives before the original message was sent. This isn't a matter of perspective or different simultaneity definitions. This is actual, unambiguous backward time travel as measured by a single observer, the loop that eats itself. Now let's trace through the causal chain and watch it devour its own tail. Event 1. Earth receives the reply message saying, "Don't send the warning." This happens first. At let's say time equals 10 years in Earth's reference frame. Event 2. Based on that message, Earth decides not to send the FTL warning about supernova X. The transmitter gets turned off. This happens at time equals 12 years. Event 3. Earth sees supernova X at time equals 10 years happening simultaneously with receiving the reply. But wait, they've already been told not to send a warning, so they don't send anything. But here's the problem. If Earth never sends the original warning, then the ship never receives it. If the ship never receives it, the ship never sends the reply. If the ship never sends the reply, Earth never receives the message telling them not to send the warning. So Earth should send the warning, which means the ship receives it, which means the ship sends the reply, which means Earth doesn't send the warning. Round and round and round we go. This is the grandfather paradox, pure and simple. You go back in time and prevent the very event that caused you to go back in time in the first place. It's logically impossible. It's a contradiction. A equals not a, true equals false. The universe breaks, and all you needed to create this catastrophe was two FTL communicators and some observers moving at relativistic speeds, ingredients that would be absolutely commonplace in any civilization advanced enough to have FTL technology. The instantaneous case makes it worse. Now, you might be wondering if maybe there's something special about the particular speeds and distances I chose for this example. Maybe if we tweaked the numbers, the paradox would go away. Nope, let's actually make the scenario simpler and show that the paradox becomes even more obvious. Imagine that instead of merely faster than light, our FTL communicators are instantaneous. The message travels from sender to receiver with zero elapsed time. On a spacetime diagram, instantaneous communication appears as a horizontal line parallel to the space axis, because you're covering distance, but not time. So Earth's instantaneous message to the ship would be a horizontal line at the moment Earth sees the supernova. Boom, instant transmission. Now, what about the ship's reply? The ship also has an instantaneous communicator, so the reply should be instantaneous in the ship's reference frame. But remember, the ship's space axis is tilted. What appears as instantaneous to the ship parallel to its tilted space axis appears as backward time travel to Earth. Because the ship's space axis isn't horizontal in Earth's frame, draw it out on the diagram, and you'll see the reply line extends from the ship back to Earth, parallel to the ship's tilted space axis. And when you look at where that line intersects Earth's world line, it's at an earlier time than when Earth sent the original message. In fact, with instantaneous communicators, the paradox becomes even more extreme. The faster your FTL, the more severe the causality violation. Instantaneous communication is the worst possible case maximum FTL. Maximum paradox. So no, tweaking the speeds doesn't help. It makes things worse. Why physicists lose sleep over this? You might be thinking, okay, this is weird, but maybe the universe can handle paradoxes somehow. Maybe causality is more flexible than we thought. Maybe there are multiple timelines, or maybe paradoxes resolve themselves in ways we don't understand. Physicists have explored these ideas. They really have. And none of them work satisfactorily. Multiple timelines. That's the many worlds interpretation. And while it might resolve time travel paradoxes in quantum mechanics, it doesn't help here. We're talking about classical objects sending classical messages. There's no quantum branching, no wave function collapse creating alternate timelines. Just straightforward cause and effect, except the effect is preventing its own cause. Self-consistency. Maybe the universe somehow prevents you from creating paradoxes by making you fail whenever you try. Maybe Earth's transmitter mysteriously malfunctions at the crucial moment, or the ship's crew inexplicably decides not to send a reply. But this requires some kind of cosmic conspiracy, some mysterious force that intervenes to prevent paradoxes. That's not physics, that's magic with extra steps. The hard truth is that paradoxes like the grandfather paradox are logically impossible. They cannot exist in any consistent reality. A universe that contains such paradoxes isn't just strange or counterintuitive, it's literally nonsensical, self-contradictory at a fundamental level. And if paradoxes can't exist, an FTL inevitably creates paradoxes, then FTL can't exist either. This is why physicists take this problem so seriously. It's not about engineering. It's not about energy or exotic matter. It's about whether the universe makes logical sense.
Hawking's bold prediction. Enter Stephen Hawking, one of the greatest physicists of the 20th century. Hawking thought deeply about time travel and its paradoxes. And in the early 1990s, he proposed what he called the chronology protection conjecture. The conjecture is beautifully simple. Time travel paradoxes are impossible. Not difficult, not unlikely impossible. The laws of physics, at their deepest level, are arranged in such a way that you cannot create paradoxes. Whenever you try to build a time machine or create a causal loop, some physical effect will prevent you from succeeding. This isn't wishful thinking. Hawking had good reasons for this conjecture, based on his work on black holes and quantum effects in curved spacetime. And here's where it gets interesting for our FTL discussion. Remember back in part 2 when we talked about the Alcubierre drive and how quantum effects specifically, Hawking radiation build up exponentially inside the warp bubble, destroying it from the inside. That's chronology protection in action. The universe is preventing you from building an FTL system by making it unstable at the quantum level. Wormholes face the same problem. When physicists try to include quantum effects in their calculations, they find that wormholes become violently unstable. Quantum fluctuations in the vacuum flood the wormhole throat with energy, pinching it off and destroying it before anything can pass through. It's almost like the universe is actively defending itself against time travel. Every time physicists find a loophole in classical general relativity that might allow FTL or time travel, quantum effects show up and slam the door shut. The missing piece of the puzzle. Now, we need to be careful here. We don't actually have a complete theory of quantum gravity yet. We know quantum mechanics, and we know general relativity, but we don't have a unified theory that combines them perfectly. Physicists have been working on this for decades. String theory, loop, quantum gravity, causal dynamical triangulation, all sorts of approaches, but we're not there yet. So when we talk about quantum effects destroying warp drives or wormholes, we're extrapolating from what we know into regimes where our theories might not be valid. We're making educated guesses, but here's the thing. Those educated guesses all point in the same direction. Every time we try to include quantum effects in calculations involving exotic spacetime structures, those effects make the structures unstable. Every single time, maybe that's a hint. Maybe the universe is trying to tell us something. Maybe when we finally discover the correct theory of quantum gravity, it'll come with an ironclad proof that chronology protection is real, that time travel paradoxes are absolutely forbidden, and that FTL is impossible because FTL equals time travel. Hawking certainly thought so. His conjecture essentially predicts that the missing piece of the quantum gravity puzzle will turn out to be whatever mechanism prevents paradoxes. The universe's defense against causality violations is hidden in that gap in our knowledge. It's a bold prediction, and if it's right, it means FTL is doomed, not by engineering challenges, but by the fundamental logical structure of reality itself. The loopholes nobody wants to mention. But, and this is important, Hawking's conjecture is just a conjecture. It's not a proven theorem. It's an educated guess based on the patterns we've observed, but it could be wrong. So let's be intellectually honest here. Are there ways that FTL might be possible, despite everything we've discussed? Maybe, sort of. With big caveats. One possibility, FTL is possible, but there are strict rules about how you can use it. In our paradox scenario, the problem arose because the ship responded to Earth's message. The ship intervened, creating a causal loop. But what if something prevents that intervention? What if the laws of physics somehow forbid sending a reply in the specific configuration that would create a paradox? It sounds contrived, and honestly, it kind of is. You're basically saying, FTL is possible, except in exactly the situations where it would cause problems. That's not very satisfying scientifically. It's like saying, you can have your cake, except when you want to eat it. But it's not completely crazy. Maybe there's some deep principle we haven't discovered yet that naturally prevents paradox-generating FTL uses while allowing safe ones. Maybe the universe has a built-in safety mechanism that's more subtle than just forbidding all Another possibility. Maybe we just accept that paradoxes can exist and figure out how to live with them. Maybe causality is negotiable. Maybe the universe is weirder than we ever imagined, and logical contradictions are somehow permissible. But this is really, really hard to swallow. The entire edifice of science rests on the assumption that the universe follows consistent rules, that effects follow from causes in a predictable way. Abandon that, and you don't just lose FTL, lose the ability to make sense of anything. So these loopholes aren't really loopholes, they're desperate attempts to save FTL by either constraining it to uselessness or abandoning logic itself. Not exactly compelling options. The definitive statement. After all the discussion of warp drives and wormholes, all the talk about energy requirements and exotic matter, all the complicated diagrams and reference frames, we finally have something definitive to say about FTL. Here it is. All FTL systems, regardless of how they work, allow for causality-breaking time travel paradoxes. Not might allow. Not could potentially allow. Allow period. Full stop. This isn't speculation. This is provable from the axioms of special relativity. You don't need to know the specific mechanism of the FTL system. You don't need to understand the engineering. You just need to accept that special relativity is correct, and we know it is, because we've tested it to ridiculous precision and the conclusion follows inevitably. FTL equals time travel. Time travel equals paradoxes. Paradoxes are impossible. Therefore, FTL is impossible. It's a syllogism, a logical argument that flows from premises to conclusion, as surely as 2 + 2 = 4. Now, you might object, but special relativity could be wrong. Maybe at extreme speeds or distances, different rules apply. And, sure, maybe, physics is always subject to revision when we discover new evidence. Newton's laws worked great until we found situations where relativity mattered. Maybe relativity will turn out to be an approximation to, but here's the thing. We've tested special relativity incredibly thoroughly. Particle accelerators routinely handle particles moving at 99.999% of light speed, and they behave exactly as relativity predicts. GPS satellites have to account for relativistic effects to function properly. We've done experiments with atomic clocks on airplanes that confirm time dilation to absurd precision. So if relativity is wrong, it's wrong in some regime we haven't accessed yet. And until we find that regime, we have to take its conclusions seriously, including the conclusion that FTL is impossible. The uncomfortable truth. This is hard to accept. I get it. I really do. Remember, at the beginning of part 1, I talked about looking up at the stars as a kid and dreaming of reaching them. That dream dies here. Not because we're not clever enough, not because we haven't tried hard enough, but because the universe apparently won't allow it. The cosmic speed limit isn't just a suggestion. It's not just a high bar to clear. It's a fundamental constraint woven into the fabric of causality itself. Breaking it doesn't just require advanced engineering, it requires breaking logic. And logic is not negotiable. So where does that leave us? Are we truly imprisoned in our solar system, forever limited to watching the stars from afar? Is the dream of galactic exploration dead? Not quite. Because there's one thing we haven't talked about yet. You don't actually need FTL to explore the galaxy. It's harder, it takes longer, and it requires a different mindset than most science fiction has prepared us for. But it's possible, and maybe, just maybe, the fact that FTL is impossible is actually a blessing in disguise. Maybe the universe is teaching us something important about what kind of civilization we need to become. That's what we'll explore in the final part of this journey. Because even if faster than light travel is off the table, the stars aren't beyond our reach. We just need to think differently about how to reach them, and what it means to be a species that explores the cosmos, not for personal glory, but for something far bigger than ourselves. Part 5. Beyond FTL, the future we can actually build. Hawking's bold prediction. Enter Stephen Hawking, one of the greatest physicists of the 20th century. Hawking thought deeply about time travel and its paradoxes. And in the early 1990s, he proposed what he called the chronology protection conjecture. The conjecture is beautifully simple. Time travel paradoxes are impossible. Not difficult, not unlikely impossible. The laws of physics, at their deepest level, are arranged in such a way that you cannot create paradoxes. Whenever you try to build a time machine or create a causal loop, some physical effect will prevent you from succeeding. This isn't wishful thinking. Hawking had good reasons for this conjecture, based on his work on black holes and quantum effects in curved spacetime. And here's where it gets interesting for our FTL discussion. Remember back in part 2 when we talked about the Alcubierre drive and how quantum effects specifically, Hawking radiation build up exponentially inside the warp bubble, destroying it from the inside. That's chronology protection in action. The universe is preventing you from building an FTL system by making it unstable at the quantum level. Wormholes face the same problem. When physicists try to include quantum effects in their calculations, they find that wormholes become violently unstable. Quantum fluctuations in the vacuum flood the wormhole throat with energy, pinching it off and destroying it before anything can pass through. It's almost like the universe is actively defending itself against time travel. Every time physicists find a loophole in classical general relativity that might allow FTL or time travel, quantum effects show up and slam the door shut. The missing piece of the puzzle. Now, we need to be careful here. We don't actually have a complete theory of quantum gravity yet. We know quantum mechanics, and we know general relativity, but we don't have a unified theory that combines them perfectly. Physicists have been working on this for decades. String theory, loop, quantum gravity, causal dynamical triangulation, all sorts of approaches, but we're not there yet. So when we talk about quantum effects destroying warp drives or wormholes, we're extrapolating from what we know into regimes where our theories might not be valid. We're making educated guesses, but here's the thing. Those educated guesses all point in the same direction. Every time we try to include quantum effects in calculations involving exotic space-time structures, those effects make the structures unstable. Every single time, maybe that's a hint. Maybe the universe is trying to tell us something. Maybe when we finally discover the correct theory of quantum gravity, it'll come with an ironclad proof that chronology protection is real, that time travel paradoxes are absolutely forbidden, and that FTL is impossible because FTL equals time travel. Hawking certainly thought so. His conjecture essentially predicts that the missing piece of the quantum gravity puzzle will turn out to be whatever mechanism prevents paradoxes. The universe's defense against causality violations is hidden in that gap in our knowledge. It's a bold prediction, and if it's right, it means FTL is doomed not by engineering challenges, but by the fundamental logical structure of reality itself. The loopholes nobody wants to mention. And this is important, Hawking's conjecture is just a conjecture. It's not a proven theorem. It's an educated guess based on the patterns we've observed, but it could be wrong. So let's be intellectually honest here. Are there ways that FTL might be possible, despite everything we've discussed? Maybe, sort of. With big caveats. One possibility, FTL is possible, but there are strict rules about how you can use it. In our paradox scenario, the problem arose because the ship responded to Earth's message. The ship intervened, creating a causal loop. But what if something prevents that intervention? What if the laws of physics somehow forbid sending a reply in the specific configuration that would create a paradox? It sounds contrived, and honestly, it kind of is. You're basically saying, FTL is possible, except in exactly the situations where it would cause problems. That's not very satisfying scientifically. It's like saying, you can have your cake, except when you want to eat it. But it's not completely crazy. Maybe there's some deep principle we haven't discovered yet that naturally prevents paradox-generating FTL uses while allowing safe ones. Maybe the universe has a built-in safety mechanism that's more subtle than just forbidding all Another possibility. Maybe we just accept that paradoxes can exist and figure out how to live with them. Maybe causality is negotiable. Maybe the universe is weirder than we ever imagined, and logical contradictions are somehow permissible. But this is really, really hard to swallow. The entire edifice of science rests on the assumption that the universe follows consistent rules, that effects follow from causes in a predictable way. Abandon that, and you don't just lose FTL, lose the ability to make sense of anything. So these loopholes aren't really loopholes, they're desperate attempts to save FTL by either constraining it to uselessness or abandoning logic itself. Not exactly compelling options. The definitive statement. After all the discussion of warp drives and wormholes, all the talk about energy requirements and exotic matter, all the complicated diagrams and reference frames, we finally have something definitive to say about FTL. Here it is. All FTL systems, regardless of how they work, allow for causality-breaking time travel paradoxes. Not might allow. Not could potentially allow. Allow period. Full stop. This isn't speculation. This is provable from the axioms of special relativity. You don't need to know the specific mechanism of the FTL system. You don't need to understand the engineering. You just need to accept that special relativity is correct, and we know it is, because we've tested it to ridiculous precision, and the conclusion follows inevitably. FTL equals time travel. Time travel equals paradoxes. Paradoxes are impossible. Therefore, FTL is impossible. It's a syllogism, a logical argument that flows from premises to conclusion, as surely as 2 + 2 = 4. Now, You might object, but special relativity could be wrong. Maybe at extreme speeds or distances, different rules apply. And, sure, maybe, physics is always subject to revision when we discover new evidence. Newton's laws worked great until we found situations where relativity mattered. Maybe relativity will turn out to be an approximation to, but here's the thing. We've tested special relativity incredibly thoroughly. Particle accelerators routinely handle particles moving at 99.999% of light speed, and they behave exactly as relativity predicts. GPS satellites have to account for relativistic effects to function properly. We've done experiments with atomic clocks on airplanes that confirm time dilation to absurd precision. So if relativity is wrong, it's wrong in some regime we haven't accessed yet. And until we find that regime, we have to take its conclusions seriously, including the conclusion that FTL is impossible. The uncomfortable truth. This is hard to accept. I get it. I really do. Remember, at the beginning of part 1, I talked about looking up at the stars as a kid and dreaming of reaching them. That dream dies here. Not because we're not clever enough, not because we haven't tried hard enough, but because the universe apparently won't allow it. The cosmic speed limit isn't just a suggestion. It's not just a high bar to clear. It's a fundamental constraint woven into the fabric of causality itself. Breaking it doesn't just require advanced engineering, it requires breaking logic. And logic is not negotiable. So where does that leave us? Are we truly imprisoned in our solar system, forever limited to watching the stars from afar? Is the dream of galactic exploration dead? Not quite. Because there's one thing we haven't talked about yet. You don't actually need FTL to explore the galaxy. It's harder, it takes longer, and it requires a different mindset than most science fiction has prepared us for. But it's possible, and maybe just maybe the fact that FTL is impossible is actually a blessing in disguise. Maybe the universe is teaching us something important about what kind of civilization we need to become. That's what we'll explore in the final part of this journey. Because even if faster than light travel is off the table, the stars aren't beyond our reach. We just need to think differently about how to reach them, and what it means to be a species that explores the cosmos, not for personal glory, but for something far bigger than ourselves.